how hello world really works, or the story of Printf. In C#, it's pretty simple, system.console.writeLine, and then your string. With Java, it's pretty simple too, system.out.println, and then your string. With C, it's a little bit different. You first have to include standard I/O, and then you just call printf, and then your string, hello world. And then you get this output. With Visual Studio, you get hello world in its own console. With NetBeans and Java, you get it in its output. So what happens is you basically take your string in your program. You send it to your library, your Java virtual machine, or the CLR. That sends it to the OS, and then the OS basically sends it to the hardware, and that's out to your monitor. So let's take a look at the source code for Printf. Printf is actually pretty simple. You take two parameters. The first parameter is the constant char star called format. That's your string. Now with C strings, they're a little bit unique. They're actually an array of characters. And the three periods are basically, in C, you can basically send any amount of arguments that you want on top of that with three periods. And basically VA list takes those three periods and plugs them into VA list. Int done is a little bit unique. In C, there are no exceptions. So basically, there are no throwing an exception and it gets called up the stack and that sort of thing. What happens is you actually have to check its return value to see if it was successful or not. And that's what done is. So int done and then vf printf, that will return an integer that will be returned by printf, and you can check that to see if it was successful or not. And then you have your main function called vf printf, and basically it sends to standard out, format your string, and then arg list. Okay? And there are format specifiers that you can do. So you can do you can take 65 and express it as a character, which is actually A. And so the little %C, that means character, %, or 4.2f, that displays a float in a very specific way. There are just some interesting things that you can do with string formatting. Which is why there's the arg on there. In Unix, everything is a file, well, except for RPCs, which are remote procedure calls. And there's a concept that you need to know about, which is called standard streams. You have standard input, which is basically all your keyboard, and then you have standard output, which is your display to your monitor. And then you have standard error, which is sometimes either separated from your display monitor or not. You can check out more at the Wikipedia article, Standard Streams. You can redirect these streams to say you want to pipe it to a file, which this command right here, ls, will pipe the directory list to directory-tree.list. You can check out more about pipes and I/O redirection. With standard stream, it allows a uniform way to output stuff and input stuff. So say you're working on an embedded system. You don't have a display, a video card, you don't have anything. What you actually want to do is send it to a serial port. Or if you're on a computer, you can send it to a file or a console or an IDE, just like Java did with NetBeans, and just like Visual Studio sent it to actual console, popped up a console window. So let's take a look at the source code for vf printf. It returns an integer, and it takes two parameters, basically a constant char star called format, which is your string, and then a VA list called arg, which is what you sent it from print. vf printf prints formatted data from a variable argument list to standard output. It writes the C string pointed by format to the standard output and replacing any format specifiers in the same way that printf does, but using the elements in the variable argument list identified by args instead of additional functions arguments. If you want to learn more about this, you can go to c++.com, standard I/O, and then vprintf. You can check out the source code of vprintf on the website here. Now you're leaving user space and you're going into the kernel. And I don't know the kernel that well. You can check out, look more up at system calls, as far as Wikipedia, kernel.org, and then there's a really good Unix system calls quick reference PDF that's available. So what it basically does is you take that string that you just did from your library, it puts it into the standard out buffer. The buffer is then processed and then actually outputted. But what we can do is write our own kernel. And a little bit about programming language. The first generation of programming languages was actually machine code, the actual things that the CPU instructions. People wrote this stuff. And then what happens is people got tired of that, and basically they created a one-to-one mapping from assembly into machine code and back to assembly. Very easy to use. It's very human readable, but not human writable. It's not really efficient. So what we did is we created a new generation called third generation programming language, like Algo and COBOL and C, where it's more human writable, but there you lose the one-to-one mapping. So what happens with C is you can turn that into machine code and CPU instructions very easily, but you can't take machine code and turn it into C. That's called decompiling, and it just doesn't really work that well. But you can take assembly and turn it into machine code and turn it into assembly. And so x86 bootstrapping is the first part of a kernel. And basically how this works is when you power on the computer, the CPU is hardwired to go to the last address of the last 16 bits of the 32-bit address space of RAM. And it will execute whatever is there. And what's there is a jump instruction to go to the BIOS, wherever the BIOS is stored in RAM. And what that does is then it starts the BIOS. The BIOS then searches for bootable devices with a magic number. At the end of the boot sector of all devices, there will be a magic number there. If there is a magic number there, it's bootable. If there's no magic number there, it's not bootable. And the magic number is 0x55 and then 0xAA, and they're hexadecimal numbers. If the device is bootable and it checks this location, what it will then do next is go to the beginning of the boot sector and boot off there, and it will load your master boot record, and you'll start the boot process into the kernel. Let's take a look at the source code to actually boot up this kernel. This right here is bits 32. That means we're going to use a 32-bit instruction set because there is a 64-bit instruction set, and there is a 16-bit instruction set. So we're going to make sure that the assembler is using the 32-bit instruction set. Selection.text this is where text comes along. Extern kmain is we can have external functions that run, and we're just saying, hey, we're going to run this function, we're going to provide it later in the C file. And then start is where the actual program starts up, and so we're now going to basically say CLI, which blocks the interrupts, so no interrupts can happen, and then basically it calls kmain, which is the C program that I'm going to show you in a minute, and then it halts the CPU. ASCII was really designed for printers, and so you have a lot of like backspace, line feed, end transmission, end text, start text. You have a lot of control characters that were originally designed for printing, and that's what ASCII was originally designed for. And you can see this is a teletype machine with Bill Gates right here. And when computers got internal video cards and hooked up with monitors, they had a completely different way of doing this, because it was basically like sending to a serial port, to your printer, or to your teletype machine, or to a terminal. That's how you'd communicate. But with a video card, you actually now have something internal that can run. And you have two modes that you can display in. You have text mode and bitmap mode. With video output, it's a little bit unique. The CPU and the graphics card share access to the same memory. Usually this is system RAM in these earlier systems. Sometimes now it's dedicated RAM. And so in text mode, you have a reserved block of memory, 80 by 25 bits long times 2, because you need 2 bits to store the attributes. This block of memory is now reserved for the video card, and you can just write to that, and the video card will refresh every time it refreshes. It will just read that memory again, and it will display the text. This is how it works. You write to memory, video card refreshes whenever it wants to, and it will display your text. You need 2 bits. You need your character that you're going to output, and then you need the attribute, the color. And so you basically individually go through each bit at the start and go HELLO space world, and that's what you do. And you can define, the text attribute that you want to. With bitmap, it's a little bit different, because now instead of characters, you have pixels. You're defining it all by the pixels. In black and white systems, you only need 1 bit, because it's either on or off. But when you want to start displaying color, how do you display color when you have very limited amounts of RAM? Because as you get more color and more depth, you start having to have more RAM. So basically you need now, say your screen resolution, which is a lot more than 85 by 25, times 3, because you need 3 colors per screen, are red, green, blue. But they came up with a simple system. We're going to use the color palette. So we're basically going to find a list of colors, and instead of having any colors that you want, you basically have like a list of 16 or a list of 256, and you say, we're just going to reference those color palettes. So let's say I want the first color in the color palette, and you'd basically put 1 or 2. I want the second color in the color palette. That's how, when you have limited RAM, you can display 256 colors. When there was enough RAM for everybody, you can now represent the full 3 colors, all your color different variations. So each pixel has 3 in RAM that you can address. So you can go to the channel red, green, blue, you set those, and then you move on to the next pixel. Now that gets into updating. When computer screens update, there's sometimes a flickering. And what you need to do is create a double buffer is the solution to screen flickering when it plays games and when it comes to a lot of interaction. Because what could happen is it could refresh right exactly in the middle or at the beginning or at the end of when you started to write to RAM the new next screen. So what you need to do is you need to trigger the refresh, have it refresh on one side of memory, so you now double it, and you have the top half, you're refreshing off the top half, you finish writing on the bottom half, and now you're refreshing off the bottom half, and you're writing at the top half of the RAM. That's how double buffering works, prevents screen flickering. If you want to learn more about this, go to Frame Buffer on Wikipedia video card or howstuffworks.com graphics card. And that sort of explains some of the stuff. Back to the code. So we have our CarStar pointer, my first kernel. That's what it's going to display. And this video pointer is the pointer to the address of where the video memory begins. And we can just do pointer math to get to the right area that we want to go to. And so, first of all, we're going to clear everything that's on the screen. And this is what does it. So 80 times 25 times 2, that's the number of bits that we do. And then we're basically going to systematically go through these bits. And we're going to place a space or an empty space there. And then we're going to set the character 0x07, which is light gray with a black background. So it would just be a black background because of the space. And then it's plus 2 because you have just written 2 bits and you just go through that entire thing. You've now refreshed your screen. So now we're going to actually write the character. With C strings, they're a little bit unique. They are terminated by a null character, which is a /0. And so basically at the end of all strings in C, there's always a /0. Otherwise you have really big problems because it will just continue until it finds a /0. So basically this string is going to go through a do a while loop, and it's going to basically output each character by character through the video pointers and setting the background as 0x07. Now there's a character there. Now it's going to be the light gray. And then you skip 2, and then it returns that, and basically then the CPU halts, and there's your results. My first kernel. That's how you output to screen, hello world.